Hello, and welcome to my second lecture on limits. This is about finding limits analytically. Now, in the previous lecture, I talked about how to find limits both graphically and numerically. But in this particular case, when we're going to learn how to find them analytically, that's a method that can be used as a proof. You can't really use numerical or graphical as proofs, but they're really good for explorations and bettering your understanding of what's going on with a particular function. So let's get started in how we're going to find limits analytically. All right, so we have some steps. First step is to just try plugging the value x is approaching into the expression. All right, you'll see examples of all of these in a few minutes. Okay. Step two is if when you plug that value in to the expression, you get a math bad thing, then you need to try to rewrite the expression by either factoring and dividing or by multiplying by the conjugate over itself. And let's talk about math bad things. I talked about math bad things there. What does it mean? Well, math bad things include dividing by 0, taking the square root of a negative number, because in this class we're only going to be dealing with real numbers, and using inverse trig functions outside their domain, such as taking the arcsine of 1.3. Since on the unit circle, when you take the sign of a number, you always get something in between -1 and +1. If you try to take the arcsine of 1.3, you're outside the domain of arcsine, because that's outside of the range of sine. All right, let's go to step 3. Now, step 3 I've just included to be complete, but at this point we won't be addressing it. It's using the squeeze theorem, or the sandwich theorem, or L'Hopital's rule. And at this point, we're not going to be addressing these. These will be addressed in a later video. And so let's get right on to doing our examples. So first, we have example 1. Example 1 is taking the limit as x approaches 2 of 3x squared. That's pretty straightforward. Just try plugging in the value that x is approaching. We plug it in. You can see it causes no problems because we get 3 times 2 squared. That's 3 times 4. 3 times 4 is 12. It's that simple. Remember, don't forget that first step. Sometimes it's really easy. Next, let's take the limit of 3x squared plus 4x as x approaches -1. Again, this is a polynomial expression, so nothing bad is going to happen. We plug in -1. We get 3 times -1 squared plus 4 times -1. And that gives us 3 minus 4 is equal to -1. Again, a really simple one. No big deal. Let's go on to example 3. Okay, so example 3 is taking the limit as x approaches -1 of x squared minus 1 over x plus 1. Now you see, when you try plugging in -1, we're going to get a divide by 0 problem here. So what we need to do is rewrite this. So we're going to take the limit as x approaches -1 of, let's factor the top. The top factor should be x minus 1 times x plus 1, a simple difference of squares. We should remember that for a later problem coming up here, over x plus 1. All right, then we cancel out the x plus 1s, and you're just taking the limit as x approaches -1 of x minus 1. So the limit as x approaches -1 of x minus 1. Now what we've done is we've rewritten that original expression so that it has an equivalent expression for all values besides the point where we had a math bad thing going on, where we were dividing by 0. If you were to graph this, it would look just like a line with a hole in it at x equals -1. And so x minus 1 is simply the line without the hole. All right, we plug in -1, we get -1 minus 1 equals -2, and that's our answer. This function is approaching -2 as x approaches -1. Go to example 4. Example 4 is basically the same thing. We just have a little bit more complex factoring to do. We try plugging in -1. We're supposed to try plugging in first. Well, we get a math bad thing. So we're going to need to factor this. Now, I don't know if any of you remember, there's a mnemonic device. It means same, opposite, always positive, SOAP. And that's what we can use to factor a sum of cubes. So to factor this, it's going to be the limit as x approaches negative 1. Remember, again, always carry down the limit notation. You don't just drop the limit notation. It's important to write it. So we take the cube root of x cubed, we get x. The cube root of 1, we get 1. Now I'm leaving out the signs for the moment because that mnemonic device is going to help us fill those in. Then to get the rest of the parts, there's a trinomial over here. Square this, we get x squared. Multiply these two together, we get x. Square that, we get 1. Now we can come back in and put the signs in. Do them in a different color for emphasis. So this is the same as the original, so plus. This is the opposite of the original, so that's minus. And this one is always positive. So again, same, opposite, always positive. Okay, over x plus 1. All right, we can cancel. And we've removed that discontinuity. So you can see that what this would look like if you graphed it would be a quadratic with a hole at x equals negative 1. So it would be a parabola. All right, now we can plug negative 1 in to what's remaining, and we would get 1 plus 1 plus 1, so that's equal to 3. Now, if you're on a part of a test where you're allowed to use your calculator, you could always use your calculator to find this limit numerically or graphically, and just to verify your answer. All right, we have one more example. So in this example, we now have a root in the denominator. Well, that's fine. I know you were told in the past you couldn't have radicals in the denominator, but that was just for convenience sake. It's actually okay to have them, except for here, if we plug in 3, we get square root of 4 is 2, minus 2 is 0, so you would get 2 minus 2 in the denominator again. You'd have it divided by 0 error. So we don't want that. Let's get rid of those for a moment. Oops. Go back to where we were, sorry. Okay, so what we need to do is multiply by the conjugate over itself. Well, if you recall from imaginary numbers, the conjugate is simply a binomial. So there's a binomial there. So it's the same binomial, but with instead of this minus, it's going to be a plus. So we're going to multiply by square root of x plus 1 plus 2 over square root of x plus 1 plus 2. Let's clean that up a little bit. It got a little bit ugly up there. Okay, so we're going to write it like that. And now, again, carry down your limit notation. People are always wanting to distribute this out because you see a binomial times a binomial like this and people want to distribute it. Well, in this case, we really don't want to. Just leave it in its factored form. Use parentheses. This is just x plus 1 plus 2 over. Now, this, when we distribute it, it behaves just like a difference of squares. Remember, a couple problems ago, we had x squared minus 1, and that factored into x minus 1 times x plus 1. Well, this is just going the other direction. So we're distributing a difference of squares, and we end up with square root of x plus 1 times square root of x plus 1 is x plus 1. Okay, and then we have negative 2 times positive 2 is minus 4. All right, so the denominator, well, I didn't write very well there. That's x plus 1 minus 1. Well, that would become x minus 3. And you can see that x minus 3 could cancel out with this x minus 3. All right, so you see why you don't want to distribute the numerator, because it would have made things ugly. As it is, things are actually pretty simple. So let's go back to our original color. We have limit as x approaches 3 of square root of x plus 1 plus 2. There's no denominator left at all. We can plug things in. We get square root of 4 plus 2, and that equals 4. All right. So that's an example of multiplying by the conjugate over itself to rewrite a radical expression so that we can remove the math bad thing. So that's the lecture on finding limits analytically. Practice a lot. You'll find out that they're not that difficult to deal with. Thanks for listening.